Hello everyone. Today we'll see a few results relating continuous functions to random variables. So let me start with the first result. So if x is a simple random variable and g is a function, let us focus on continuous function because that's what we need. In general, the result is true for other functions also, but we would assume continuity. And g is a continuous function, then gx is also a simple random variable. As I said, we are actually not going to use continuity at all. So we can simply say g is a function, still the result holds. Okay. So x is a simple random variable means what? Let me just define the notations first. So x is defined from omega script a to rb. X is a simple random variable means x can be written as sum over ai, indicator ai, I going from 1 to k, where ai's are real numbers, small ai's are real numbers, and capital Ai's form a partition. Forms a partition of omega. Okay. Now, what we know is g is some function. So, we can say that g of ai, we can give it a notation bi. Okay. Because g of ai is going to be a single value. Since g is a function, ai would go to some particular value. Let me call it bi. Of course, some of the bi's may be same, but still without loss of generality, I can write g of x as sum over I going from 1 to k g of ai into indicator capital AI. I am not applying g to both sides of this equation. Okay, that's not what I'm doing. See, what I'm doing is, this is suppose my omega, and this is say a1, a2, a3, a4, a5. Okay, a1, a2, a3, a4, a5. Now on this region, value of x is say a1. So of course on this region, when I consider gx, its value will become g of a1. Similarly, on this region, value of x is a2. So when I apply g to all these points, it would become g of a2. That is exactly what we are writing here. Okay. So g of x can be written as sum over g of ai into indicator of capital AI. And g of ai we can call as bi. So this is nothing but a representation of a simple random variable. In fact, the partition stays same. Whatever was the partition for x, that same partition is working for gx. Okay. Therefore, gx is a simple random variable. Okay. So we have proved that if x is a simple random variable and if g is any function, then gx is a simple random variable. We are going to need this result in our next proof. So our next theorem says that if x is a random variable and g is a continuous function, now we need continuity here. We will see in the proof why do we need continuity. So if x is a random variable and g is a continuous function, then gx is also a random variable. Okay. If x is a random variable and g is a continuous function, then gx is also a random variable. Now how do we prove this? We are going to use the result that we proved just now, and we are also going to use the results that we studied yesterday. So yesterday we had a result that if x is a random variable, then there exists a sequence of simple random variables xn. There exists a sequence of simple random variables xn such that xn converges to x pointwise. We saw this result yesterday. Okay. So same thing we are going to use now. Now this x is a random variable, so there exists a sequence of simple random variables xn such that xn converges to x. Now since every xn is a simple random variable, by the result that we proved just now, gxn is also a simple random variable. Correct? We proved this result just now. Now what can I say about the sequence gxn? Because g is a continuous function, since g is a continuous function, we know the property for continuous function that if there is a sequence of real numbers an converging to a, then for a continuous function gan converges to ga. This is property of continuous function. Here if we fix omega, then x and omega is a sequence of real numbers. We saw this yesterday. For a particular fixed omega, x and omega becomes a sequence of real numbers. And what I know is x and omega converges to x omega. Okay. Therefore, by the property of continuous function, g of x and omega converges to g of x of omega. Okay. Now, what I know is xn is a simple random variable, g is a continuous function. Okay. And hence we know that gxn is a simple random variable. Therefore, gx becomes limit of a sequence of random variables. Are you with me so far? Gx becomes a limit of sequence of random variables because these are all simple random variables. Okay. And we saw a couple of lectures back that limit of a sequence of random variables is also a random variable because limit is actually lim_sup or lim_inf, and lim_sup and lim_inf can be written as supremums and infimums, etc. Okay. Therefore, gx is a random variable. Since it is limit of a sequence of random variable, it becomes a random variable. Okay. So what we have proved is if x is a random variable and if g is a continuous function, then gx is also a random variable. Okay so far? We have already studied one result related to random variables and their functions. So we have proved that Borel functions of random variables are random variables, right? Borel functions of random variables are random variables. We have proved it. And now we are saying that continuous functions of random variables are random variables. So there has to be some connection between continuous functions and Borel functions. So that is our next result. So now we will prove that every continuous function is a Borel function. Okay. We'll prove that every continuous function is a Borel function. Of course, there are many discontinuous functions which can also be Borel function. But if a function is continuous, then we don't need to check about its Borelness. It is already a Borel function. So we will prove this result now. Okay. So let g be any arbitrary continuous function. We need to prove that g is a Borel function. If I want to prove g is a Borel function, what do I need to prove? I need to prove that inverse image of every Borel set under G should be again a Borel set. Okay. So that means we have to prove that G inverse of S belongs to script B for every S in script B. Okay. So what we are going to do is we are going to use the result that we proved just now. So we proved that continuous function of a random variable is a random variable, and it's a random variable means it is Borel measurable. Okay, so consider a particular random variable. G has to be arbitrary because we have to prove for every G. So I can't choose G and say it is true for this particular G. Okay, but for this proof I can choose X of my convenience. So consider X as an identity function. Okay, consider a random variable which is an identity function. So G of X omega would become G of omega by this definition. And by earlier result, we know that G of X omega is a random variable. G of X omega is a random variable means what? We know that if you have Gx and if you take inverse image under Gx of any set, then it becomes a Borel set. Okay, since Gx is a random variable. Correct? And now, what is inverse image of under Gx of any set in this particular context? Because Gx is G, because you are taking X as identity random variable, X omega is just omega. So Gx inverse becomes just G inverse. Okay. So Gx inverse becomes just G inverse, and hence we have proved that G inverse of S is in B for every S in B, because this was also true for every S in B. Hence we have proved that every continuous function is a Borel function. Okay. Hence, if we have a continuous function, we don't need to check about its Borelness. Continuous function of a random variable will again be a random variable. Okay. So, we will stop our discussion on random variables here. Now we have to introduce the probability measure, and then we'll study a few properties of distribution functions. Okay. Thank you.